Hi, everybody. Welcome to Sage Talks Medicine. Today, we'll be reviewing a question based on the Hardy-Weinberg principles. This is a very important step one topic that might show up on your test, and it's often very confusing. So, I hope to break this down. Now, let's look at the question. A 2-year-old infant presents with hypoglycemia, hepatomegaly, lactic acidosis, and seizures after fasting. This condition is caused by deficiency of glucose 6 phosphatase. In a population where 1 in 2,500 individuals has this condition, what is the probability that two healthy, unrelated individuals will have a child affected by it? Now, if you want to work this out, you can pause the video here and come back when you're ready. Okay, welcome back. So, in questions like this, the first step is identifying the condition so that we can determine whether it is autosomal dominant or recessive, and based on that, we can calculate the frequencies. So, this condition is von Gierke disease. This is a glycogen storage disorder type 1. Now, patients with this condition present with severe fasting hypoglycemia. They have a buildup of glycogen in liver and kidneys. They have high blood lactate levels, and you have high triglycerides, high uric acid, hepatomegaly, renomegaly. The liver does not regulate blood glucose. It's all caused by a deficiency of glucose 6 phosphatase. So let's say your body needs glucose. It's going to break down its glycogen stores. And unfortunately, for these individuals, we're unable to release the glucose as we're breaking down glycogen. And so it basically gets stuck at the glucose 6 phosphate step, and you're unable to remove the phosphate from the glucose. And the treatment for this condition is frequent oral glucose, cornstarch, avoiding fasting, avoiding fructose, lactose. And again, you have impaired gluconeogenesis. You can't make new glucose, and you have impaired glycogenolysis because you're unable to break down glycogen. Now, going back, although it doesn't say in first aid, we know that this condition is autosomal recessive. Okay, so that's the first thing that we need to write down. Okay, it is autosomal recessive, and that will help us kind of have a step forward of what to do. So it's autosomal recessive. Now, Hardy-Weinberg, I'm going to go back to the first aid page. Now, all of this looks very daunting. I'm not going to read all of this, but basically, Hardy-Weinberg is a set of principles and assumptions that are set in place that makes it easy for us to calculate frequencies of genotypes and alleles. And what they're assuming is that mating is random and the allele and genotype frequencies are constant. Of course, that's not the case in real life, but these set of assumptions help us calculate the best approximate frequencies. So assumptions include no mutations happening, natural selections not happening, completely random mating, no net migration, and a large population. So, for Hardy-Weinberg, you want to know two main equations. If you understand that, you're good. So, the first one is P plus Q equals to 1. Now, what the heck is P and Q? Now, P and Q are alleles, right? They're a version of a gene. You get one allele from mom, one allele from dad, and let's say there's two different types or versions of a gene. Now, P and Q. So, in a population, the frequency of one allele, one version of the gene, and the second allele, the second version of a gene, when you add them together, you'll get one. It's one whole, right? So this is alleles. Okay, allele number 1 and allele number 2. The second equation that you need to know is p squared plus 2pq plus q squared equals to 1. Now, why are we saying 1? Because in a population, there's going to be individuals that are going to be p squared. Now, this talks about genotypes. Genotypes are the pairs of alleles that the person has, okay? So mom and dad came together and they produced some individuals with p squared. Now, what does p squared stand for? It's people that are homozygous dominant. So let's say capital A is one allele and lowercase a is another allele. So these individuals that are p squared are going to be capital A, capital A. And what does that show? That shows that these are homozygous dominant. Okay. Next, we're going to have 2PQ. These are individuals that are heterozygous, meaning they have two different versions of the gene. So allele, sorry. So it's going to be capital A, lowercase a. Now these are our heterozygous individuals. And finally, we have Q squared. These are individuals that are lowercase a. And what is that? This is homozygous recessive. Homozygous just means you have the same version. And this is the recessive. Okay? So now we got two equations. We got the allele version of it and we got the genotypes. Okay? Now going back to the question. So the question was basically we there's two parents, they're healthy, right? But they could be carriers. Okay? So we want to find, and another assumption that you make in Hardy-Weinberg is that if it is a rare autosomal recessive disease, we assume that P, the dominant allele, is equal to 1. Okay? That means in the population, it's like most individuals they have the dominant normal version of the gene, okay? So we're gonna assume that P equals to 1. Now, we want to figure out if the parents are carriers, okay? And what is the likelihood of that? Okay, because they're not affected by this disease. So what we do is we know, so which equation can we use? We want to find the carrier status. So we want to see the heterozygous individuals. So we are going to go with this. Okay. So now, before we do that, actually, we want to figure out at least one, we want to figure out what is P, what is Q. So we know that P equals to 1 because remember we said that in a population, and if it's a rare condition, the dominant form of the allele will be 1. We don't know what Q is, but we can figure that out. So it says in a population where 1 in 25 individuals has this condition. So that means that these people basically, or this question gave us what this is. Homozygous recessive. They gave us this already, okay? So let's go back. So they gave us that 1 in 2,500 people, this represents Q squared. These are the people that have one Gierke or Gierke, I'm sorry for the pronunciation, but they have the condition, okay? So how do we solve for Q? Okay, we want to get rid of the square, so we're going to square root this, that comes out. So Q equals to 1 over 50. Okay, so if we figured that out, good. We know P equals to 1 because that was part of the assumption. So perfect. We know what P is. We know what Q is. Now we can literally figure out anything, okay? So in a Hardy-Weinberg question, first we figure out the condition, okay? And whether it's autosomal dominant, autosomal recessive, most likely it's a recessive one because those questions are more interesting. Then we figure out what is P and what is Q. We know that from the assumption that P will always be 1. If it's a rare condition, we know that P is 1. And Q usually you can be found because in the question they give you the frequency of people that have the condition, and that represents Q squared. Okay, so we found out what P is, we found out what Q is. Now we've got to figure out what is the chance that these two parents that are healthy that are carriers, okay? So again, we're going to use 2PQ, okay? So what is the chance that they're carriers? So it's going to be 2PQ. That is the chance, okay? So that equals to 2 times 1 times 1 over 50. Now, with USMLE questions, it's very rare for Hardy-Weinberg that you'll need a calculator. It'll be questions that can be easily worked with, you know? So you can cross that out. That's 25. So that's equal to 1 over 25. So the chances of one parent being a carrier is 1 over 25. Okay, so we found that out. Now I'm running out of space, so we're going to add one more paper to this. Okay, so now we figured out what is the chance of one parent being a carrier. So now what is the chance of two parents being carrier? So it's going to be 1 over 25. And in probability, every time what is the probability of this and this happening? The and is always multiplication, and or is a plus. That's just a side note. But okay, so 1 over 25, 1 over 25. So that is going to be 1 over 625. So this is the chances of two parents being carriers. Now, are we done with this question? No, because now we've got to figure out what is the chance that when two carriers come together, that their child will be affected. So how do we do that? Now, I hope you remember Punnett squares. It's easy for me to do that at this point. So let's assume that parent A is capital A, and the other parent's capital A, lowercase a. You make a Punnett square. We love this here, super easy. Um, okay, so the chances of the child being affected is 1 over 4. Okay, so now you have two probabilities. Okay, so one more step and we're almost done. So what is the chance of the, so we, what are, so now in this question where we have two probabilities. Basically, the child will be affected if the parents are carriers and they get a child that is affected. So remember, whenever there's an and, you want to multiply. So it's going to be 1 over 625 and 1 over 4. So basically, we want to say this is the chances of the parents being carriers and then the child being affected. So the probability comes to about 1 over 2500. Now let's go back here. Okay, so the right answer was 1 over 2,500. So I know this seems a little like all over the place, but I'm just gonna now talk about how to approach this question. Let's say you come across a Hardy-Weinberg. What we did in this question was first, we figured out we figured out the condition. Okay, that's step one. What is the condition? Because that will test your knowledge of genetics and your knowledge of picking up what the like diagnosis from the presentation. We're gonna see, okay, is it autosomal recessive, autosomal dominant? Next, we are gonna write down the two equations. So P plus Q equals to 1, and P squared plus Q, sorry, I was getting a little too excited. 2PQ plus Q squared equals to 1. And we want to figure out, and we usually, if it's a rare condition, it's going to be P equals to 1 almost. And Q, we could figure that out if they give you, in this question, the number of people affected. And you can figure out Q from Q squared equals to this, and we solve for that. And then we use these two equations to find the rest, essentially. And just remember, if this question that I presented is a little complicated because you have to calculate two probabilities, right? You have to calculate the probability of the parent being a carrier, and then you have to calculate the probability of the child being affected. So I would say this is like the most complicated type of question that you'll see on step one based on Hardy-Weinberg. Most of them won't be as complicated, but this is a variation that I've seen during my practice. So again, you want to calculate the carrier situation. So, and then you want to calculate if they're a carrier, what is the probability that their child will be affected? And remember that whenever we say and, the probability of this and that, it's going to be multiplication. Okay. So I hope this was helpful for you all. And let me know if you guys have any questions in the comments below. I hope this was clear, and I hope to bring you more questions like this so we can break it down together using first aid and my personal experience doing thousands of questions during my own practice. I hope you all have a wonderful day. Take care.